So aromatics are a specific class of organic compounds, and they have a specific set of characteristics that they have to meet in order to be considered aromatics. So this is it's a class of compounds. Right. And the criteria to be considered aromatic, um, there are four criteria. And we're going to talk about those in a second. But one thing that's common to all aromatics is this, is that they have pi bonds that are in resonance with one another. That is a consequence of the fact that they are fully conjugated. Another, and this is not the criteria, this is just some characteristics of, I will talk about the criteria shortly, but these are some characteristics of aromatics. They are unreactive without a catalyst. Right, and they're also cyclic. So most of your aromatics are going to be cyclic compounds. So we got a few more people. Let me put this handout in the chat again. All right, so they have pi bonds that are in resonance, and a lot of times you'll see an aromatic ring written. I'm just going to give you the most basic one, benzene, like this. And so the double bonds are immediately alternating. And you can also think about this, excuse me, with these double bonds being in resonance like this. Right, and if we drew the resonance form for this, right, it would look like that. So a lot of times you'll see this written as a Kekulé structure, which just has a ring in the middle, like a circle. And that circle is indicative of those electrons just constantly moving, constantly being in resonance. All right. And then sometimes you'll see, so this is benzene. There are other aromatics. We're going to look at some examples shortly. And sometimes you'll see this if the aromatic is a substituent, like a benzene ring. So we have something like this, where the benzene ring is here, right? We can abbreviate that, and we call this a phenyl group, right? And it's abbreviated as pH. So this would be 1, 2, 3, 4, 5, 6, 7. So 3 phenyl heptane, right? So when the ring is a substituent, we call it phenyl. If it's just a benzene ring, now of course there are other aromatics that can be substituents. So benzene is a substituent, then we call it a phenyl group. So, and a lot of times you'll see that abbreviation often. especially in large molecules where space is a premium when you're trying to write out the whole molecule. You'll see that those aromatic rings abbreviated as pH. All right. So again, aromatics, they are different class of compounds. They're very unreactive. They are all of them are fully conjugated, cyclic, and those pi bonds are in resonance with one another. Right. So we talked about fully conjugated versus non-conjugated already, or partially conjugated. We talked about that already. So let's look at I'm going to cut this out actually and put it on a separate page. And then we can discuss it without having to jumble everything up. All right, so up above this image, above the images, these are the criteria for aromaticity, right? They have to be flat, in other words, planar, monocyclic, meaning consisting of one ring. And there are some exceptions. Obviously, the second example right here, naphthalene, is an exception to that. Right, this was the principal component in mothballs before they switched over to something else. Some of y'all might not be old enough to know what mothballs are, but if you got a grandparent that's over 70, you probably know what they are. Also have to meet the 4n plus, and we're going to discuss each one of these criteria individually. So you have to meet the 4n plus 2 rule, which applies to the pi electrons that are present in the system, and must be fully conjugated. Right, so let's talk about the planarity part first. So if you look at a system, like all of these systems are planar. What that means is that, all right, the ring is a flat system. If I were to draw benzene in 3D, right, it would look like this. I put the pi bonds in, and planarity is a requirement for conjugation in these rings. Right, what you'll notice is that those pi bonds and those p orbitals that make them up, right, if they're planar like this, all those p orbitals can see each other. So planarity so that's required for orbital overlap. Right, you have to, that's why that's a requirement for aromaticity, because if the orbitals are not overlapping, then the conjugation is going to be disturbed, right? So a system like this down here, you can see right away when I put the p orbitals into this system, I'm going to put them in everywhere there's a pi bond, there's 2 p orbitals. You can see right here, so these orbitals right here are all fine, right? They can see each other, talk to each other, overlap, all of that. But the orbitals down here on this part that's bent down, because of different steric effects, the larger your ring is, the more kinks it's going to have in it. I'm saying that as an oversimplification. But with this ring right here, you can see that these p orbitals right here are not lined up with the p orbitals in the top part of that system. So I'm going to draw that like that. And I'll draw this one like that. Right. So these p orbitals down here, pick a different color. They're out of alignment. Right. So the rest of that pi system cannot overlap with those p orbitals that are facing perpendicular to it. And so because of that, that's a problem, right? And so that breaks up the planarity, and it also breaks up the conjugation. So this is non-planar and not fully conjugated. Right. So a system like this, even though it looks like it should be aromatic, is not, because it's not, it doesn't fit the planarity criteria, nor does it fit the fully conjugated criteria. Right. So planarity, that's a requirement in order for those orbitals to properly overlap, see each other, and in order for the conjugation to be possible. All right. So if we look at each one of these, let's take each one of them through the same test. Right. So let's take, so let's take benzene, for instance, and let's ask the same, all four of those questions of benzene. So here is benzene, and we already know that it's planar. All right. We already know that it is monocyclic. It's only made up of one ring. All right. Is it fully conjugated? What is that? What's the definition of being fully conjugated? Somebody help me out right there. We just studied that, by the way.
Alternating single and hybrid.
Well, you can have that and not be fully conjugated. Being fully conjugated is you're right. That's part of the definition. But the full definition is having a p orbital on every carbon. That's what we said that something was fully conjugated. Then that means that every carbon in that system had a p orbital, right? And you can see here, I'll draw them in again. Every one of these carbons has a p orbital on it. So it is fully conjugated. All right. Now the last question, well, the third question, I skipped over the third question, but that's very important. The worksheet is on Blackboard. It's in Aromaticity. It's in assignments, and then it's in the folder labeled Aromaticity. All right. So let's talk about the 4n+2 rule. Right. That's one of the main criteria for being considered aromatic, is to meet the 4n+2 rule. And so what the 4n+2 rule is, basically you set the number of pi electrons equal to 4n+2 and solve for n. N has to be a whole number, right? So for benzene, this is a 6 pi system, right? There are 3 double bonds and 2 electrons in each double bond. All right, so this is a 6-pi system. So we're going to say 4n plus 2 is 6. And then we solve for n will be 1. So as long as n is a whole number, then we can say that that system meets the 4n plus 2 rule. All right, if n is not a whole number, then it doesn't meet the 4n plus 2 rule. And in order for something to be considered aromatic, every one of these criteria have to be met. All right, so benzene is the perfect molecule, right? All the bonds are the same length. It's conjugated, so it's low in energy. I mean, it's the perfect molecule. And it's aromatic, so that's even better because the aromaticity also contributes to how low the energy of that system is. All right, so benzene is aromatic because it meets all the criteria. Let's take a look at naphthalene. So we'll look at each one separately. And remember, these are the criteria. That is flat or planar, monocyclic, it meets the 4n plus 2 rule, and it's fully conjugated. We know already that naphthalene is an exception. So we're gonna give it a pass on the monocyclic requirement. We'll give it a pass on that because we know that it's an exception to the rule. All right. But now let's ask the other question. Is it planar? Right? This is if you had a model set and built this, you'll find that naphthalene is a very rigid bicyclic system. So it is planar. There's no flex or give or rotation around those bonds in that ring whatsoever. So it is planar. It is an exception, so we're not going to worry about it being monocyclic. Let's look at the conjugation and whether or not it meets the 4n plus 2 rule. So it is planar. All right, so how can we determine if it's fully conjugated? What would you do to see that?
You would
Me-
see,
Say that one more time.
you would see if there's a P orbital on each carbon.
So let's put in the p orbitals, and then that'll tell us. All right, so we got a p orbital here, one here. Everywhere that there's a double bond, that's 2 p orbitals. Right, and you can see for this molecule, right, that there is a p orbital on every carbon. So the question of whether or not it's fully conjugated, the answer is yes. All right, so that's aromatic. It meets all the criteria. Let's take a look at, oh, wait a minute. We didn't do the 4n plus 2 rule. How many pi electrons are in this system? In order to answer that question, all you do is take the number of pi bonds that you see and multiply by 2, because there are 2 pi electrons in every pi bond, just like there are 2 electrons in any bond. So how many pi electrons are here? Good. Got 10 pi electrons, so we're going to set that equal to 4n plus 2 and solve for n. In this case, n is going to be 2. Is that right? So as long as n is a whole number, it meets the 4n plus 2 rule. So naphthalene is aromatic according to the rules. All right.
I have a question.
Go ahead. I was just about to open the floor up for questions, but go ahead.
So even though it's not monocyclic,
Mhm.
it'll be.
Oh yeah, yeah, it's still aromatic. There's some other exceptions. Anthracene is another exception. Anthracene is basically a 3-ring fused system, but it's even though it's not monocyclic, it still meets the criteria for being aromatic.
I have a question.
Go ahead.
So I thought being monocyclic was one of the rules.
Yeah, it is, but there are exceptions to that rule.
Oh, okay.
Yeah, so naphthalene is an exception. And then this let me fix these double bonds that look sloppy. This compound here, anthracene, is also an exception. So you do have an exceptions to the monocyclic rule, but as long as the other criteria are met, then we can live with it not being monocyclic, because really the aromaticity is based on that conjugation and how those orbitals are able to overlap. And even in a planar, even in a multi-polycyclic system like naphthalene or anthracene, what we notice is that it's still pretty rigid. Those systems are rigid. They don't have much give in them at all because of those pi bonds. So even with that, the p orbitals are able to overlap, right? In the whole system, you got p orbitals on every single carbon. So that's really a very extended level of conjugation, but all those p orbitals overlapping like that, right? And so because of that, that's what holds the shape. So even though it's polycyclic, it's so rigid that you can consider it to be monocyclic. All right, that's a good observation. All right, let hope that answered your question too.
Yeah, thank you.
Okay. Let's look at the next molecule, because that cyclopentadiene anion is a derivative. We have to derive that, right? So let's look at where it came from first. Let me fix that. So this is cyclopentadiene. Cyclo because of the ring, penta because it's 5 carbons, diene because it has a diene here, right? So it is, if we look at cyclopentadiene by itself, is that aromatic? All we have to do is apply the test, right? Is it planar? Most of your rings past that are less than 10 carbons are going to be planar. Then you get there's a space in between 10 and about 10 and 15 where the ring starts flopping around because of transannular effects. And then after that, it goes back to being planar, right? But most of your small rings like this are planar. So this is planar, it's monocyclic. Is it fully conjugated?
No.
No.
No, it's not. And what you'll find out also is it doesn't meet the 4n+2 rule either. And we can figure that out pretty quickly. 4n+2 is going to be 4. N is going to be a half. So it's not a whole number. So it doesn't meet the 4n+2 rule. And it's not fully conjugated. So we got a problem. But we can make this aromatic by doing a proton transfer with a strong base. So let's pick one of the bases we're already used to seeing. Let's use potassium terbutoxide, which is we learned about when we did E2 elimination, right? Very, very strong base. And when we use that base, that's going to give us come on, Russell. So there's still a hydrogen left here. The potassium is hanging out here because it's a ionic charge. Ionic. I don't know where's that. You keep disappearing. Something right over. I'm not sure why that's happening. Let me just move it over. That's one of them. All right, so that's that plus terbutanol, right? So that proton that got pulled off here ends up here. All right. So now this is a very versatile intermediate, a very versatile compound, to be honest. This is used a lot, especially in organometallic chemistry as a ligand for many different types of catalysts. It's abbreviated as CP, but it is the cyclopentadienyl anion. Right? And when we look at that, it's different from what we started with. What's the difference?
You lost the hydrogen.
So you lost a hydrogen. What did you gain?
Pair of electrons.
A pair of electrons. Good. So now let's go back through the criteria. Is this planar?
Yes.
Planarity didn't change. It's still a flat 5-member ring. It's still monocyclic, right? Is it fully conjugated now? Let me draw it out in 3D. Well, kind of like 3D. So that lone pair that's now on that carbon, we can put it in a p orbital. It's still negative, but we can put it in a p orbital. And every one of these p orbitals has one electron in it. So now what you notice now is that there is now a p orbital on every one of those carbons. And that wasn't the case initially. Right? So now it is fully conjugated. And it meets the 4n plus 2 rule. How many pi electrons are there now? It was four pi to begin with. We added a pair. I think I heard you say it. Tia, did you say 6?
Yeah.
Yeah, you're right. So this is 4n plus 2 equals 6. N equals 1, which is a whole number. So now this is not aromatic. But the anion is. If you can actually derive aromatic compounds like this pretty simply. The pKa of that proton that's highlighted, well, both of them, because they're equally accessible and equally susceptible to being doing proton transfer. The pKa of that proton is somewhere about 15, which is almost the same as an alcohol proton. So that you can pull that thing off easily. all you need is a pretty decent base, and potassium terpbutoxide is excellent base. So you can deprotonate that and make that anion with no problem. All right. Any questions about this example and its aromaticity? All right. Let's do the last one, and then we're gonna move on, and we're gonna discuss a first reaction, which is a halogenation. We'll talk about the mechanism and how that mechanism applies to all of these aromatic reactions. All right. So let's go to the cycloheptatrienyl cation. So we're going to start out with cycloheptatriene, which is a 7-member ring. I hate drawing 7-member rings. All right, and in this ring we have 3 double bonds, and we have some hydrogens here, right? All right, so cycloheptatriene. Is that aromatic? It is planar. 7-member rings are planar. It is monocyclic. It meets the 4n+2 rule. It's got 6 pi electrons. It looks like 27. All right. The question is it fully conjugated?
No.
No, it's not. It has p orbitals on these carbons. No. But that's it, right? It does not have a p orbital here. Right, so it's not fully conjugated. There's not a p orbital on every carbon. But we can fix that. If we take this and remove a hydride, right, so H minus, we get rid of H minus, right? That's going to create a cation, right? That other hydrogen, let me put the hydrogen back in. I don't want to spook you. The other hydrogen is still here, right? And now that is a cation because I took off a hydride and so a hydrogen and a pair of electrons. So now that's positive. So can you see now everything, all the other criteria were already met. What I have now in that cation is an empty p orbital. Right, so that cation, which is here, it's now going to overlap with all of the other p orbitals in that ring, right? And so because of that, now it's fully conjugated. So the cation is fully conjugated. So all the other criteria still stick. Now it's fully conjugated. So the cation of cycloheptatriene is aromatic. This is not aromatic. All right. And let me write in the name if I can fit it. Right, so this is another case where you can actually derive the aromaticity. It's not inherent in the molecule, but through some chemical manipulation, you can get to it. All right, any questions about that example?
I have a question.
Go ahead. Can you get a little closer to your mic or speak up a little bit?
Yes. So if it's not fully conjugated,
Mhm.
all you have to do is just remove one of the hydrogens.
Depends now. It depends on what the system actually looks like. For this one, if we had put in a pair of electrons instead of making it a cation, then it wouldn't have met the 4n+2 rule, because I think n would be 8 in that case. And so it wouldn't meet the 4n+2 rule. So it's really based on what the needs are. So in this case, we needed another p orbital, but we didn't need electrons. So that's why we took off H-, right? So we took the hydrogen and its electrons and removed it to make that a cation and put an empty p orbital on that carbon. In the other example, we needed electrons because we didn't have enough pi electrons, right? So that's why we took off a proton in this case and left behind the electrons, so that those electrons would be in a p orbital that would overlap with the other 2 pi bonds. Does that make sense? So it's kind of case by case, depending on what the needs of the system are.
Okay.
All right. Good question. Great question, by the way. Excellent question. All right. Now let's take these reactions. We're gonna go through them one by one. I think we're only gonna have time to do the first one. So we'll just go over that one and then we'll pick it back up on Monday, God willing. Let's go back to, let's move another page. Ooh, why my iPad sticking? Money for another one. All right, so with aromatics, when they do react, it's only under really specific circumstances that they react, right? You have to really, you have to beat on aromatics to make them do any type of reaction. And they do not react outside of a catalyst. You have to have a catalyst present. Most of the times, a metal catalyst or some other type of electron donor like sodium or some other catalyst to get these things to go. So, but the reactions all follow the same pattern. So anytime you have a reaction with an aromatic, it's gonna all those reactions gonna follow the same basic mechanism. The first step is going to be preparation of the electrophile. The second step is going to be attack. Attack of the aromatic ring on the electrophile. And then the third step is going to be to reestablish aromaticity. And every one of these reactions is going to follow the same mechanism. So reestablishing aromaticity is the most important step here, because aromaticity gives so much stability that that's why these rings don't react. It's almost like people, right? You don't see people who have things relatively together. You don't see them going and doing crazy stuff, going out, jumping off mountains and jumping off buildings and things like that. Stability actually matters, right? And so the more stable a system is, the less reactive it's going to be. And so anytime these things react, one of the last step is always to reestablish that aromaticity and get that stability back that was lost by through at the second step. All right. So when we look at these reactions are classified as electrophilic aromatic substitution. Right. So in this particular case, the ring is the nucleophile, is written down here. So the ring is going to act as the nucleophile. And then the substitution part, if you notice, I added a bromine here. What I substituted was one of the hydrogens. Right, so that's the substitution part. So electrophilic, meaning that I'm adding an electrophile. Aromatic, I'm adding it to an aromatic system. And then substitution, which means I'm substituting one of the hydrogens on the ring with bromine. So let's look at we got 3 minutes. Let's look at how this works, right? So all of these reactions follow the same paradigm where you have the first thing that happens. So iron is your catalyst. Can somebody define what a catalyst is? Anybody?
Is that speeds up the activate, or it lowers the activation energy?
Good. Lowers the activation energy. And the other part of that is that it's never consumed, right? It's not a reactant. It's just there to lower the activation energy by activating one of your substrates and then making it more reactive or less or more susceptible to reaction. And then by the same token, at the end of the cycle, it gets regenerated. Every catalyst is always going to be regenerated at the end of the reaction. So this first reaction is halogenation. The first step, so let me just rewrite it. So we got this going to this. And we use Br2 and iron bromide, iron 3 bromide. Right, so the first step is preparation of the electrophile. So we take the Br, and then that is actually going to coordinate with iron. So you get this iron bromine complex. The way it coordinates, obviously, it has some lone pairs around it. Right? So then this bromine becomes partially positive, and now that's my electrophile. Right? So now in the second step, that's when the ring attacks. So we prepare the electrophile. All these reactions follow the same path. Prepare the electrophile first, attack with the ring, and then reestablish aromaticity. So when the ring attacks this, I'm gonna use this double bond right here. right? This is going to attack like this, boom, like that, and then you're going to break that bromine bond. Let me just, right? So from that, we're going to get this, and this is a very important intermediate that I'm getting ready to show you. Right, so the iron tetrabromide is now negative, and then you get this cation, which we're going to call an rhenium ion. Right, that's common to all of these electrophilic aromatic substitutions. Is this rhenium ion? All right. Then in the final step, that's when you reestablish aromaticity. Because right now it's broken, right? It's disturbed because the conjugation is all messed up. There's a charge in the ring, so it's no longer aromatic. Right, so the way you do that is just to do an elimination. So you take the iron tetrabromide, which is negative, and a pair of electrons is going to come here and eliminate, put a pi bond back there. So you're left with the ring with the bromine now attached to it, plus HBr, plus the catalyst. And the catalyst can go back and do the same thing over and over and over and over again. And every time your catalyst gets regenerated, it's called a turnover. So every time you go through the cycle once and regenerate the catalyst, it's called a turnover. So depending on how good the catalyst is, some catalysts can give you 1,000 turnovers, some can give you 1,000,000 turnovers. It just depends on what type of catalyst it is. All right, we got to stop there. I apologize for going a little bit over time, but I'll see you on Monday, God willing, and we're going to go through the other two reactions. And I'm also going to send you a video with the dealing with aromatics with the mechanism, so you'll have a chance to reinforce this. And if you look in the syllabus, the section in the book on aromaticity is listed with problems. Also, if you don't have the book, well, you got the syllabus, but if you don't have the book, you can Google it, right? There's no shortage of resources about this topic. All right, any questions?